All right, so here we have two ice puck, one orange, one blue. They have equal masses, and it involves in a perfectly elastic glancing collision. So glancing collision essentially just says one ricochets off in an opposite direction as the other one. So here it says that the orange ball's initial or orange puck's initial speed is 5.05 in the statement. And then the theta at the very top of the horizontal axis here is 40 degrees. And it wants us to determine the speed of each puck after the collision. All right, let's go ahead and crack this out. So first I'd like to point out that they're equal masses, so I'm just going to call this orange puck M because that's M. The blue puck is also going to be M. And then in addition to that, the given statement says that the initial speed, or velocity in this case, of the orange puck is to the right at a rate of 5.05. So I'm going to label that. And then the blue puck was initially at rest because it said so. And then the angle theta here at the top where the horizontal axis in the orange puck is 40 degrees, then that's given. And then because it says perfectly elastic, in a perfectly elastic, when masses are the same, the other angle has to add up to 90. So I'm going to go ahead and label this by deduction. This is 50 degrees. Okay, so it's important that you don't assume things always add up to 90. It has to state that the masses are equal and that it's perfectly elastic. Other than that, you cannot assume that the two angles add up to 90. So be careful with that assumption. All right. So here, I'm just going to start with the x direction and move my way to the y direction as usual. If you see my other videos here, I'm just going to say momentum in the x direction is initially equals to momentum in the x direction on the final frame. Here, I drew the V orange F here in this particular problem. O for orange, F for final. So here is the component of VOF. So that'll be VOF in the x direction. And likewise down here, we have VBF, but VBF is a diagonal in the southeast quadrant or direction, so it has to have a component pointing right and down. So I'm just going to go ahead and focus my attention in the x direction now. So VBF also has a VBFX that's pointing right. So right away you notice, just using common sense here, both these stats are going to be moving to the right of the screen. So therefore both of these horizontal momentum components are in the positive direction. Okay, so here initially the only object that I have moving is the orange puck. The blue puck was initially at rest, so the only momentum in the x direction to start is the orange puck because it is moving to the right at a rate of 5.05. And then to the right, we have two pucks moving off in the first and fourth quadrant, or northeast and southeast. So therefore, I am going to use the V orange F in the x direction, and then likewise with the V B for blue here, FX. Okay, so just kind of separate information to F and X and Y direction, and then just stick with it. Here I'm going to cancel mass out because it appears in every term, and for this one, once again, it says equal masses. So be careful with the algebra here. Don't just cancel mass out unless it's the same. So here on the left side, you notice we have V naught IX, which is given as 5.05. I know that value already. The one thing I don't know is VF naught X, okay, and VBFX, but I can quickly do a substitution here. So on the bottom of my screen, I'm just going to show you this one time. This way you can kind of keep up with the geometry. So here I trace out VOF, and that is the vector given in northeast quadrant. So I just kind of made a right triangle representing the orange puck here in the final frame. So here I'm just going to label things. This is theta, that's given as 40 degrees. And then this is V orange final, and then this is going to be V orange FX. So I'm just going to draw a triangle just to show you where the components are, or how to find them. Okay, so here cosine of theta according to this particular right triangle is by definition adjacent over height, but as you can see in this particular right triangle, the adjacent is V orange final in the x direction. The hypotenuse is V orange in the final here. All right, I'm just going to replace it with what I know. The adjacent is VOFX. The hypotenuse is just VOF. And then to solve for VOF, I would simply multiply both sides by to solve for VOFX, I would multiply both sides by VOF here. So therefore, we can say that the final horizontal component of the orange puck is simply the hypotenuse, which is given as VOF times cosine of theta. And we can use the same strategy for the y component. So the y component would be the same thing really, except it's sine theta because the angle is touching the x-axis here. Okay. All right, so let's go ahead and replace stuff we know. So VOIX is just 5.05. I left the units out just to save some space here. VOFX, I don't know, but if you kept up here, I just show you how to find VOFX just by setting up a right triangle. So instead of VOFX, I replace it with this true statement, VOF, and then the x is simply cosine of 40 degrees. And likewise with VBFX. So I'm going to use the same strategy. So VBFX here would also be cosine, but the angle here is 50 degrees instead of 40. Okay. So hopefully you understood the geometry here. If not, spend a little time there, and then once you do that, keep up with the rest of the work. I'm going to simplify cosine of 40 degrees on my calculator. That gives you about 0.766. And then I'm just going to write the coefficient in the front. That's all it is. So here is VOF, cosine of 40, but cosine of 40 is 0.766 VOF. Likewise with the right side here, cosine of 50 is about 0.643 on your calculator. And then I just move VBF to the right side just to keep the coefficients in the front. So as you can see here, we have two unknowns, and as usual, if you have two unknowns in one direction, set up the other direction so that you can unlock this problem. Okay, so let's go ahead and set up the y direction. Here, the initial momentum in the y direction must equal to the final momentum in the y direction. But as you can see here in the diagram, before collision, there was no momentum in the y direction. Orange puck is moving in the x direction, and then the blue puck was initially at rest. There's no y direction. So I'm just going to go ahead and set up my y component for VFY here. That is pointing upward, so I'm just going to label that VOF in the y direction. That's pointing upward. However, if you look at the blue puck here, the blue puck is moving in the southeast quadrant, so it's going to go right and down. So make sure you draw your components with the right arrow, otherwise you can jack up your work. Okay, so you notice here my my VBFY, excuse me, is pointing downward. So that'll be negative. So it's important that you get your signs correctly. All right, other than that, I have one moving upward, one moving downward, and those have to cancel out because it starts out with 0. So I need the same number, equal magnitude, but opposite direction. Okay. So in my statement here, the net momentum in the y direction initially is just 0 because nothing was moving in that particular direction. In the final frame though, I have this orange puck that has a VFY component, and then likewise I have a VBFY that is moving downward. So you notice here in my work, instead of adding, I'm actually just going to go ahead and subtract because I know VBFY is pointing down. So I'm going to go ahead and introduce my negative sign right away just so I don't forget later. So I'm going to say positive minus negative because one is pointing up, the other one's pointing down. Okay, so as you can see here, mass cancels out again, so you can factor out an m, and then 0 divided by m is just 0. So really, the only thing you have left is just VOFY minus VBFY. I'm just going to move this negative VBFY to the other side of the equal sign, which will change sign. So now I have two positive quantities to play with. So as you can see here, you can either plug VBFY or VOFY in. Okay, so we're going to go ahead and substitute this out for what it is. In the diagram, VBFY here, watch where my cursor is, VBFY. Okay, so this down here, this angle is 50 degrees because it's giving us 50 degrees, and this is going to be your sine, right? So it's going to be hypotenuse times sine. So that's what I did there. So it will just be VBF. So instead of the subscript y got replaced with sine of 50 because that is the opposite leg. And likewise with the right side of here, VOFY is now just VOF instead of the y subscript. The y subscript now represents sine of 40 because it is a component. All right. So we have two of the same unknowns. We have VBF here, VOF. Likewise with the x direction, we have a VOF and a VBF. At this junction, you can solve for whichever you want. You can solve for VBF first or VOF first. It doesn't really matter. It'll work out. So here, I'm just going to go ahead and simplify once again. Sine of 50 and sine of 40 onto my calculator. Sine of 50 is just the opposite of cosine of 40, which I already know is 0.6766. Or you can just punch in your calculator, okay? And likewise, sine of 40 is just the opposite, it's the same as cosine of 50 degrees here. All right, so plug this in your calculator, and here, you can just solve for whatever. But I'm just going to go ahead and keep my VBF because it's already on the left side. It equals to something, so to get VBF by itself, I'm just going to divide both sides by 0.766 here. And now I'm just going to simplify this on my calculator, so I'll get about 0.84 VOF, okay? So VBF is 0.84 VOF. Now that I know what VBF is, I can just do a quick substitution here. So there's a VBF. I don't know what VBF in the x direction. I just found it using the y information. So now I'm just going to substitute it out. So here, the left side hasn't changed, so I'm just going to carry that down. The 0.766 VOF hasn't changed. I'm just going to carry that down. But VBF now is 0.84 VOF. So if you take your calculator and you take 0.643 times 0.84, you'll get about 0.54, and it is now in terms of VOF. Okay, so that's what I did in case you got lost there. Literally, I just took these two coefficients, times it, and then get that number, and then now it's in terms of VOF. Now that we have this statement, you notice that there's only one unknown, which is VOF. So I'm going to combine like terms. 0.766 VOF plus 0.54 VOF will give you 1.306 VOF. And now to get VOF by itself, just divide both sides by 1.306, which I did here. And then VOF will give you an answer of 3.87 meters per second. So that's that. Okay. And it says speed. It says speed here. Why? Because the direction is already given to us as 40 degrees. So the velocity, the final speed of the orange puck will be 3.867. The final velocity, if you were asked to find velocity instead of speed, you would say 3.867 meters per second, 40 degrees northeast or 40 degrees above the positive x-axis. Okay, so watch for wording speed versus velocity. All right, on that, now that I know the orange puck's final speed, I can use that information and find the blue puck's final speed, because I'm asked to find each puck. So I can't just stop here, and I got to do one extra step. So we already have a function for VBF, right? The final speed of the blue puck is just 0.84, so 84% of whatever V orange puck is. So we already found a VOF, which is 3.867. That's where the substitution comes in. So I highlight that yellow. I think that's our answer here for the orange puck. And then the 0.84 stays outside. So you plug this in your calculator, 0.84 times 3.867, you'll get about 3.248. And that is the speed for the blue puck. Okay, and that's the question, because it's just to find the speed, and I just found the speed of each one, and that's it. All right, stay nerdy, don't be whack.